Hi everybody, this is Mr. Zarzak, and in this screencast, I'll be discussing the optical phenomena of the mirage. The mirage would not be possible without refraction, and if you remember, refraction is a phenomena where a light wave will change speed, and as a result will be observed to bend. So let's get right to it. Some people have the misconception that a mirage is a myth, but as you can see here from this picture taken from the Mojave Desert, mirages are very real and they're also very common. If we zoom in a little bit to this picture, there's some clues that we can garnish from the picture itself to help us understand what's going on here. All right, the first is that we can see that there's an upside down image of this tent. The second thing is that there appears to be some blue here along the base. Now that blue is actually coming from the mountains in the background. The misconception is that a mirage is some kind of a reflection, but that's not true at all. Okay, what we're actually seeing here is refracted light. And so how does that work? Before we can understand how we can view a mirage, we should take a minute to think about how we see any image at all. So let's start by imagining ourselves standing on the ground, looking at a tree off in the distance. Normally, light just travels in straight lines, and we take this for granted. What I mean by this is if we want to focus our vision on the top of the tree, we look towards the top of the tree. If we want to see the bottom of the tree, we focus our vision towards the bottom of the tree, and we assume that light travels from the tree straight to our eyes. We call this our line of sight. Whether we realize it or not, this idea that light travels in straight lines is so programmed into the way we perceive the world that we never question it. If an image of a tree comes straight into our eyes, we assume that the tree is right in front of us. Just like if we want to see the clock at the front of the classroom, we turn our eyes towards the front of the classroom, because that's where the clock always is, because light travels in straight lines, except when it doesn't. So when would light not travel in a straight line? To help us answer that question, let's talk a little bit about why mirages as some kind of myth are often associated with the desert. Now, it's true that mirages do occur quite often in the desert, but it's not the only place that they occur. All right, the real criteria has to do with the air that's above the ground. A mirage can occur when you have a layer of hot air very near the surface with cooler air above. This makes mirages the most often occurring in the late afternoon on hot days. The reason you get this layer of hot air near the surface with cool air above is because the ground is heated by the sun throughout the day, but then when the sun starts to go down, air cools faster than liquids and faster than solids, and so the surface of the ground remains hot when the air cools off, much like if you've ever tried to run across asphalt or pavement on a really warm day in your bare feet, you know this to be true. All right, and so what happens is that the ground kind of acts like a heating element, almost like the burner on a stove or coals in a toaster, and it keeps the air right above the ground really warm compared to cooler air above. All right, well, why is that important? Think about a hot air balloon for a second. By heating the air inside the balloon is able to rise up into the air. Well, how does that work? If we could peer inside the balloon, and more importantly, if we could see individual air molecules, what we would see is that with warmer air, there's actually less molecules for every square meter of space. In other words, hot air is less dense than cooler air. This makes the air inside the balloon lighter than the air surrounding it, and as a result, the balloon literally floats on top of the denser air that surrounds it, just like a boat floats on top of the water that's around it. Now, we learned back in our sound waves unit that sound waves actually travel faster on warmer days than they do on cooler days. And well, the same is true for a light wave. A light wave will actually move faster through hot air than it does through cool air. Now, that fact right there, that's the really important part. All right, because try to imagine a light wave now passing from cooler air to hotter air. As it does so, it'll speed up. And technically, that's refraction. Light changing speed is refraction, and if the light moves from cooler air into warmer air at some angle, it will be observed to bend as it does so. So now think about it like this. Light's reflecting off the palms of this tree in all directions. Some of that light gets directed down towards the ground. And if it weren't for this hot air, the light would just travel in a straight line towards the ground. But because of this hot air, the light winds up bending along this path like this and actually winds up refracting up into our eye. If we think back to some of our earlier conversations about refraction, you might remember that when light moves into a faster medium, it's actually the wavelength of the light that changes. All right, well, picture it like this. Okay, so here's a rough sketch of the wavelength from one light wave to the next. Do you see how the light towards the bottom of my wavefront hits the hot air first? And so it's that part of the wavefront that's going to get that extended wavelength. So the separation between the two black lines near the bottom of my picture becomes a little bit bigger than the separation of the lines at the top of my picture. And this process continues, and it's the result of this that we get this turning. All right, so we move down into the hot air, and that wavelength continues to be a little bit longer there than up above, and so we get this gradual turn, this gradual bend to the light, enough to where it's actually redirected not from down to the ground but up to our eye. Now, remember from before, all right, we take it for granted that light travels in a straight line because, well, usually it does. But when it doesn't, that's when weird things start to happen. We look down towards the ground and we expect to see, well, the ground, and instead we see this light being bent up and towards our eye that's producing this image of the tree. And so what do we perceive? Well, from our perspective, we think that we're seeing a tree down here because we take it for granted that light should be traveling in a straight line up to our eye. But the reality is what we're seeing is this refracted light. And so this is what we would see from our perspective looking off towards the tree. We turn our eyes towards the ground and we expect to see desert sand, and instead we see this refracted image of a tree coming up towards our eye. And that right there, that's a mirage. So just to summarize, okay, the actual light coming from the tree is refracted or bent up towards our eye. The bending that occurs all comes from this process of refraction, of light changing speed as it moves from up in higher air to down, or up in cooler air to down to hotter air. And because we take it for granted that light travels in straight lines, from our perception, we think we see the image of the tree down here, when in reality it's just the refracted light moving up into our eyes. And that right there is the phenomenon known as the mirage. And although they happen often in the desert, they're by no means constrained to just the desert. Really, any place where we've got warm ground to create a layer of hot air above and a layer of cool air on top of that, conditions are ripe for a mirage. In fact, I'll bet you a lot of you have seen mirages and not even realized it. Here's a mirage of a car driving down the road on a hot day. The next time you're driving down a long road that's flat on a warm day, look to the distance. Maybe you can see one. Here's another image of a mirage, and I think this one speaks nicely to the misconception that the mirage is some kind of hallucination to where you think you see water where there's no water, when in fact what you're really seeing is refracted light of, well, the sky above. This is one of my favorite mirage pictures taken at Edwards Air Force Base on the dry lake bed where they used to land the space shuttle. Again, what looks like shimmering water is really just refracted light coming from the sky above. There's all kinds of optical phenomena that occur during sunset, and one of them is mirages. You can see here the bottom of the sun appears to bulge out when that's actually just light being refracted up along the surface of the ground. Mirages can happen on land, but they can happen on water too. All you need is some nice warm water. So a lake in the summertime, or maybe you take a trip to the Caribbean or Hawaii and maybe you'll see a mirage at sunset too. Maybe you already have. Although at first it's kind of difficult to tell what we're looking at here. This is one of my favorite pictures of a mirage. What we're actually seeing here off on the horizon is an inverted image of the buildings from downtown Chicago taken on a warm summer's day. And so mirages are very real and a lot more common than most people think. Mirages really are a phenomenal example of refraction. This is Mr. Zarzak, and I hope you've enjoyed the Glenbard West Physics Mirage Screencast. Thanks for watching.